In this segment, we'll finish our prog5.s example by looking at main, down near the bottom, mostly via a series of in-lecture questions, like the prior segment. Before we start with ILQs, however, there are a few details that you should know. First of all, recall that GCC sets up code that calls main. This setup code is the true starting point. For instance, it's where a _start label might be found. It's the true starting point of the program. So main behaves like any other called function in setting up and tearing down a stack frame. And the second point, scanf. Let's talk about that for a bit. Scanf, like printf, takes as its first argument a string, but that boils down to taking a first parameter that is the address of the string, or to be very exact, the address of the first % in this particular example. Unlike printf, however, the following parameters are also addresses: the address of each variable into which the data is to be read. Scanf needs variable addresses because it needs to know where in memory to put the data that it reads. Also, by the way, GCC will translate that scanf call, moving back to the assembly here, to a call of ISO C99 scanf down here on line 66, and that's a particular scanf version. Okay, with that background, then here are a few questions. Question 1. What do these lines here do, the first three of them, 59 through 61? Recall earlier mention of the push pseudo instruction. The answer is they store the FP and LR onto the runtime stack. Remember that push is the same as STMFD SP exclamation point. They reset the FP to point to the base of the new frame, and then they reserve forwards of local variable storage, resulting in the pattern we see here for the stack frame. Okay, so now what do lines 62 through 64 do? Note that they precede the scanf call. That's important. So can you deduce from them what variables are stored in what order in the stack frame? Well, they're setting R1, R2, and R3 to addresses within the local variable area by offsetting from FP, subtracting from FP, preparatory to passing them as parameters to scanf. Since the second, third, and fourth parameters are val A, val B, and val C respectively, this means that those variables appear in that order in the runtime stack with val C on top. To clarify that, the storage of computation, of the address in F1 is for val A, R2 is for val B, and R3 is for val C. So those offsets of 12 less, subtracting 12, 16, and 20 from FP indicate then that those variables are at these locations here in the frame. And there is one more space not yet used directly above LR here at FP minus 8. So question 3. How about the LDR R0.L7? What's that about? And can you replace it with a version that doesn't use .L7? Well, the answer is it's getting the address of the format string at LC0, and down at the bottom L7 has that value, but then as we know from prior discussions, we could have replaced this with a equal.lc0, and that would let the assembler create the address holding word. Apparently the GCC doesn't like relying on the assembler, and so it prefers setting up its own word holding or address holding words. So next question. The call of scanf is obvious enough, but what are these lines after it doing? Lines 67 through 70. And how did values get into those memory locations that we're loading there? Well, the answer is they're setting up the 3 parameters of the max of 3 call. And they're copying val A into R3, val B into R1, val C into R2, and then moving R3 back into R0 so that in fact val A will be in R0, B in R1, and C in R2. And we could obviously have made that a bit more efficient by simply moving straight into R0 at line 67. As we've seen before, sometimes non-optimizing compilers can be dumb. And the values that got into the memory locations, or the values got into the memory locations, because scanf put them there. It used the addresses we passed up here to do stores into those variables when it read in data. Question 5. Now, once we've called max of 3 here, what does this store R0 fp minus 8 accomplish? And what variable is in memory location fp minus 8? Well, remember that R0 has the return value of max of 3. It's the max value. And the instruction stores this into the one remaining open space in the stack frame, which apparently contains variable max. And then finally, what's going on with these lines here, 73 through 75? And the answer is that they load R0 and R1 with printf parameters, and they call printf. R1 in particular is loaded from, as you can see, max. And then R0 gets the address of the max is %d format string. And in this case, apparently, the compiler is fine using an equal pseudo instruction. So finally, question 7. The lines move 3 on line 76 all the way down to line 79. What are they doing? And yes, by the way, the first two are just more compiler stupidity. That could have been a move R0 #0. Make a reasonable guess as to what pop does, by the way. So the answer is these lines are returning from main. Main returns a 0 value. So that goes ultimately into R0. And then the code changes SP to point just above FP in the stack, which was where it was after the initial push instruction. And it then does a pop, which is an LD-MFD SP shorthand. It copies the LR and old FP values into FP. The old FP goes into FP, and the LR goes into PC, which effectively does a return to whoever called main.